Hi, my name is Sam,
My name is Emmett.
and we represent the University of Portland Robotics Club and the 2019 University of Portland RMC team. Here's a brief outline of our presentation. We'll be walking through the introduction of our team and our RMC history at the University of Portland, the 2018 RMC participation and evaluation results, the 2019 team design goals, our project management that we implemented this year, the design process and our philosophies, our innovation that we implemented this year, and finally we'll conclude with the safety plan and a demo. At the University of Portland, our club is made up of a multidisciplinary undergraduate club of mechanical engineers, electrical engineers, and computer science majors. We're supported in part through the NASA Oregon Space Grant Consortium, and in total we have about 3 years of participation in the robotic mining competition. Last year, our team attended the 2018 RMC competition. At that competition, we had used the previous team's robot, and we kept several of their systems. We kept their frame, the drivetrain, and the rocker bogie suspension system, but we redesigned that year the bucket chain, which was our excavation system, and the auger, which was our deposition system, as well as other various redesigns of the software and computer science. At the 2018 competition, we came in 18th place, which our team was significantly proud of, but this year we set our goals for top 10, which is what a lot of our design and performance goals will be based around this year.
In order to meet that goal of being in the top 10, we set a bunch of performance goals for ourselves. So as you see, most of these goals are actually based around our mining performance, as we were very satisfied with our performance on the systems paper and the presentation last year. So some of the most important mining related goals for this year were meeting the maximum excavation depth of 45 centimeters in order to maximize our regolith. And in order to do that, we wanted to travel to the mining area in under a minute. This would allow us the most amount of time for digging. And finally, the most important new performance goal is fully autonomous operation, because we know that would get us in the top 10.
So over the summer of 2018, we set out a rigorous schedule to complete all systems for our new robot. And the way it basically breaks down was the first semester was the mechanical and the electrical semester, and then the second semester was testing of the mechanical and electrical systems and development of the computer science.
Here's a breakdown of the funding we used for this semester. We used a bunch of parts from the old team, but we also got a lot of funding from the associated student body of our school and from the Shiley School of Engineering. Further funding came from the Oregon Space Grant Consortium, and together they funded our team for this year. It's important to note that this year's costs do not include travel to the net competition. So now I'm going to get into a little bit of the design that we did and the changes we made for this 2019 robot. There are three main systems that go into this. We have the mobility system, the excavation system, and the deposition system. First and foremost, the mobility system is made up of our rocker bogie suspension, which highlights our articulation motors and wheels, which allow individual control and drive of each wheel. In our excavation system, we utilize a bucket chain, and finally, in our deposition system, we have a brand new conveyor belt, which includes a rail extension system, allowing us for maximum deposition of material. Allowed for driving directly over the obstacles in the obstacle area in order to more quickly get to the mining area, a goal specifically set for us in our systems engineering paper. As you can see, our rocker bogie system bears many similarities with NASA's Curiosity rover. That is completely intentional. The rocker bogie suspension system, currently constructed of carbon fiber and CNC'd aluminum components, allows us to traverse up to 30 centimeters of obstacles, which was another goal set aside in our pre-systems engineering. The main component that makes this system work is our articulation joints, as you can see in the top right. These joints allow the wheels to start in a packed position, which means that they are stored underneath the robot during transport, allowing the whole system to fit inside of the predetermined area requirement. In this video, you can see a demonstration of the rocker bogie system moving at close to its full extension. This is an early prototype of the robot, but includes updated components from the 2018 to 20.
Now we'll talk about the excavation and deposition systems for this year's robot. For the excavation system, we went with the bucket chain, but we made several updates. And then for the deposition system, we switched from the auger last year to now a conveyor belt system. Earlier in the year, when we were deciding whether or not to even switch away from the bucket chain, we did a decision matrix comparing a bucket chain, an auger, and a bucket wheel. But it's clear from our decision matrix that the bucket chain was the best option, mostly due to its volume of excavation and its relative size. As I mentioned earlier, the bucket chain system is something that we used last year at the competition that we had moderate success with. So we implemented just a few updates to make it an even better system. We implemented dual Z-axis motors, which we previously only had one. We implemented a chain tensioning system to prevent stalling, a high torque motor with custom gearbox to provide plenty of torque, and finally we optimized our buckets to be made of high strength steel and plenty sharp for the IC regolith. Next, we have our deposition system. So as I said last year, we used a hopper and auger system, and then when we compared that in our decision matrix with a conveyor belt, it was very clear that we should go back to a conveyor belt. This also is influenced by the use of conveyor belts by many other teams and their success at the competition last year. Unlike the excavation system, the deposition system had to be completely built from scratch. So in our conveyor belt system, we use a mesh BP1 filter surface. We have dual internally mounted drive motors, 100 centimeter regolith deposition height, high torque lead screws, extension and retraction system. So this allows the conveyor belt to start inside the frame of the robot and then extend outwards. And then finally, we have about a 20 kilogram regolith load capacity when fully loaded.
So now we're going to transition from talking about the mechanical systems to the electrical and control systems. Our robot uses a Raspberry Pi 3, which talks to two Arduino Megas. We use an electrical box on each side of the robot for a simplified, redundant system. Each side of the robot features, like I said, an Arduino Mega, but also the motor controllers, the encoders, and the safety systems such as power loggers and fuses for each side of the robot. To control our robot, we use Robot Operating System, also known as ROS, to receive commands from our computer and direct those commands to both Arduinos. The Arduinos are subscribed to the Raspberry Pi's commands and are able to implement those commands to our individual electrical boxes. This uses the state machine and data transfer protocols currently seen. Although not currently ready for this year's competition, we've spent a lot of time this semester working on fully autonomous operation. Above is a state machine flowchart which describes how our fully autonomous system is going to work once it's been fully implemented. We're really looking forward to having this done and ready for next year's competition.
Here you can see a comparison between our CAD model and our final integrated system. So we completed the main mechanical and electrical components by the end of our first semester, so early December. And you can see here the robot on the right up in its testing rig position, ready for the computer science team to begin implementing code. Here you can see a table of our expected versus our actual results. So something to note is the mass. We wanted to be below 70 kilograms. We're actually above that at 78.2 kilograms, but this is still okay as it's underneath the competition requirements. Our maximum excavation depth is something that we reached, but actually our robot is able to excavate at even greater depths, but we're actually limited by the competition pit. Autonomous operation, we have not received any points in that category yet, as our computer science team is still implementing that code. Finally, something to note is our travel time to the mining area was quicker than we'd expected, and this actually we think will be significant in our ability to collect more material. So our club this year had a couple of innovative experiences, is what we call them. The first is that we collaborated heavily with the University of Utah and the University of Washington RMC teams. This meant that we Skyped at least once a month, if not more often. We had a very active Slack channel where we shared papers, pre-systems papers, STEM outreach papers, as well as technical ideas. For example, the University of Utah wanted to implement a rocker bogie suspension system, so that's something that we could help them out with this year. We thought this was a great experience and something that we actually think is pretty missing from the RMC experience is cross-collaboration between teams. The second one is we're from the University of Portland in Portland, Oregon, but we traveled all the way to southern Utah, where we tested our robot in the deserts there in a more Martian-like environment.
A technical innovation that we're really excited about is this year's electrical boxes. I say boxes because, like I mentioned before, we have 2 of them. The part that's really exciting for us is the modularity of them. We custom designed and printed PCBs strong enough to handle our high current loads, but with quick connect and disconnect Molex connectors. This allows us for rapid prototyping and iteration because we're able to plug in motors as we have them ready and always be testing and improving our electrical connections and systems. This also allows us to extend the life of our boxes and change them if we want to add or change parts of the robot in the future.
Now for our demonstration safety plan. This is something for all participants to keep in mind, as safety is of the utmost importance during our demonstrations. Everyone will adhere to the safety practice during the entirety of the demo. No one is to enter the robot's clear zone while it's in operation. The robot will be manually controlled via a laptop to show all of its functions. One designated person will be allowed to enter the clear zone to power on and electrically stop the robot. If the robot must be demonstrated by hand, the power will be turned off for demonstration. And finally, a video will be shown if the robot is unable to perform live. Here are some of the features on our robot that allow us to meet these safety standards. One is the implementation of a large, easily accessible emergency stop that's directly on top of the robot frame. We have short burn fuses to disconnect power on high current motor stall. Shielded wires to protect from entanglement and disconnection, and finally an enclosed and grounded electrical boxes on both sides.
Unfortunately, our robot is not currently able to perform live, so we would like to refer you to our proof of life video in order to see all features of our robot in action.